Assalamualaikum and good evening. Welcome to the 8th International Conference on Intelligent and Advanced Systems, ICIAS. Before we proceed, allow me to introduce myself. I am Nasrin and I will be your host for today's plenary session. ICIAS 2020 is Department of Electrical and Electronic Engineering, University Technology Petronas, and the theme for this year is Enhance the Present for a Sustainable Future. Due to the COVID-19 pandemic, this will be the first time that ICIAS is brought to you virtually. So this means that we would be having speakers and presenters streaming from all over the world. To kick off our plenary session, I would now like to invite the Chair of the Department of Electrical and Electronic Engineering, UTP, to deliver his welcoming speech. Please welcome Associate Professor Dr. Muhammad Naufal Muhammad Sa'ad.
Assalamualaikum warahmatullahi wabarakatuh, and a very good evening to everybody. And for those who view us from around the world, good morning, good evening, and good afternoon. I would like to welcome everybody to the International Conference of Intelligent and Advanced System, or ICIS. And as the Chairman of Electrical Electronics Engineering Department, I'm very proud to have all of you here. I would like to thank the presence of our plenary speaker, Mr. Abdul Razak Dawood, Chief Executive Officer, Energy Commission Malaysia, and another plenary speaker, also Professor Mamra Betayen, University of Sharjah, United Arab Emirates. And of course, this conference will not be a success without the key person. I would like to give a big applause to our chairman, Associate Professor Dr. Nur Shahriza Muhammad Noor, the co-chairman, Dr. Nasrin here, co-chairman to Associate Professor Dr. Tang Tongbun, Madam Inshira, Dr. Michael Ilani, and all the members, Fahmi too. So this is a huge preparation need to be done, especially to face the pandemic time. We in EE department, this department have established, when it started, it was ICIS, then we become ICIAS. And it's been a long journey for our conference to be successful until today. We're proud to have so many speakers throughout the years of this ICIS and all these papers that already published in IEEE Explore. It's a great honor because a lot of our staff, they are really attached to IEEE. So here at the department nowadays have two programs. We talk about electrical electronics engineering program and also computer engineering program, the most recent one, the young one, but that give a lot of opportunities nowadays to all our youngsters. I'm so proud because these are something that we are not only talking about academic, but also on research. We have different opportunities nowadays for these two areas. We have students that go for internship in Malaysia and also international companies, either they are in Malaysia itself, but also we send our students overseas. Our EE students nowadays are very demanding. I'm so happy to have that. And of course, without this collaboration, sometimes we found all these collaborators from this conference. So that's why it's important for us to use this stage, this platform, in order for us to collaborate, to build the best network ever. Because from this conference and a lot of other conferences and also networking, we managed to send students. We have collaboration in research. We have visiting professors from other countries, and our staff also have been appointed as visiting professors in several countries, such as France, Germany. When we have the latest one linking with us are from Turkey, new universities, of course, because we already have some old universities already linking with us. Of course, we have from UK, US, Australia. So this is something that we are very proud of, and we are happy to share all of this with you. And we hope, we also hope that all these 3 days, this conference will give you a lot of opportunities. Use these opportunities not only to expand your network, expand your research knowledge, also expand in a lot of things as a whole. Because Some of us come from industry, some of us from academy. We want to make it a strong connection during this conference time, despite having all of us have to face this pandemic time. To finish, I would like to once again thanks to all of you, those who are here. Thank you, all spectators. Thank you to all the participants, the papers presenters, and so on, and all the people who are here, and especially all the organizing committee once again and the keynote speaker. Enjoy this conference, and once again, thank you. Selamat datang virtually to Malaysia, and hope you have the best conference ever. Thank you. Assalamualaikum warahmatullahi wabarakatuh, and good evening.
Thank you, Dr. Naufal, Chair of the Department of Electronic Engineering UTP, for the very warm welcoming speech. Before we start the plenary talks proper, I would like to inform the audience that the question and answer session will begin immediately after each plenary talk. You may use the live Q&A button located at the bottom of your browser and type in your questions during the talk itself. Due to time constraints, we can only select some of the questions to be answered by our speakers at the end of the talk. We thank you for your kind attention and cooperation in this matter. Now, before we invite our first plenary speaker to take the stage, allow me to give a brief introduction on our esteemed speaker. Mr. Abdul Razib Dawood received his BTech National Diploma in Engineering from the Coventry Technical College before graduating with an electrical engineering degree from the University of Warwick, UK in 1994. He later received an MSc in Power Electronic Engineering from the University of Manitoba, Canada in 1996. Mr. Abdul Razib has more than 20 years' experience in the energy and power industry. His career includes stints in both Malaysian and Australian national power utility companies, independent power producers, TNSP, and as a consultant for renewable energy. His professional highlights include being the head of electricity market operations with the Energy Commission from 2012 to 2017, then as CEO of Malaysian Nuclear Power Corporation. In 2018, Mr. Abdul Razib joined the Energy Commission as Chief Operating Officer before being appointed as the Acting Chief Executive Officer a year later. Since August 2019, Mr. Abdul Razib has been the CEO of the Energy Commission and is responsible for the overall administration and management of the functions of the Energy Commission. With such vast technical and leadership experience, we are delighted to have him deliver his talk entitled Peninsular Malaysia Generation Development Plan 2020 from 2021 to 2039. Please welcome Mr. Abdul Razib bin Dawood.
Thank you, Madam MC. First of all, I would like to thank the organizer, UTP, and the co-organizer for inviting me personally, as well as I'm representing as well Energy Commission of Suruhanjaya Tenaga of Malaysia to speak to all of you today on the plan, what we have planned for Malaysia moving forward from 2021 to 2039. Recently, we uploaded this summary of the report. You can go to our website, www.st.gov.my. You can download a summary of this plan, what we call a Peninsular Malaysia Generation Development Plan. We do this on annual basis. You can upload information freely. So we want to share with you our role as energy regulator, or to be specific, the role of Energy Commission is to regulate these two sectors, electricity sector or power sector, as well as the gas pipe line sector, the gas that go through the pipe in Peninsular Malaysia, as well as in Sabah. So that's our jurisdiction, except for Sarawak. So that's our major roles and responsibility. So one of our major responsibility is to advise the government, policymakers, in terms of how the country should plan ahead in meeting the demand of electricity. So how we should we plan ourselves in 10 or 20 years down the road to meeting the growing demands, electricity demand or power demand, to be specific. So I will not touch upon other energy like transportation, other primary energy. So I will only talk on electricity sector for Peninsular Malaysia. So in this case. Okay, the first slide, please. All right. So in this plan, which was approved by the cabinet back in October 2020, so we have this committee. So this is under our electricity market model. We centralized planning model. So we have the committee chaired by our minister, where we sit regularly every year to look at the plan and approve the plan, and we bring forward to the cabinet meeting to get it approved. So this plan cover for 20 years. So the plan provide projection of electricity demand growth with the consideration of the economic parameters and emerging trends. Yeah, we cannot avoid, the demand of electricity obviously will follow the GDP of the country. And also we cannot deny the technology, the innovations. There are a lot of emerging trend in terms of in generation of electricity as well as in delivering electricity. So that will be one of the criteria that we look into. And also the plan provide projection of generation capacity requirement to meet demand, and important that we ensure the supply is adequate, and we have to maintain security of supply as well. Next slide, please. Yeah, I think you have seen this, what we call a dilemma, triangle, or trilemma, to be specific, energy trilemma. So we have to strike a balance between energy security, energy affordability, as well as sustainability, environmental sustainability. So this is difficult task to, especially in our role, advising the government how to program power development going forward. So we have to consider balancing this. Sometimes it can be a competing objective between security, affordability, and sustainability. That's why our role is to strike the right balance between these three objectives. So energy security you can describe as to enhance or to make sure the power or electricity that we supply is reliable, efficient, and affordability. You make sure the consumer that eventually pay for this investment, the fuel, and all those costs along the value chain is affordable, and as well as the other stakeholders in the industry, the producers of electricity. So they also want to have sustainable business venture. And the last one, environmental sustainability. We have these pledges. We part of a COP21 country, that we signed these pledges that we have to meet the carbon emission intensity target by 2030, 45% reduction with base of 2005, baseline 2005. So these are the objectives. That I always say that they keep us awake, and maybe not every night, but most of the night. So we have to think of these three objectives. Next slide, please. So we were rated by the World Energy Council recently, as recent as 2020. Malaysia ranked overall number 33 out of 108 nations in terms of World Energy Trilemma. You can download this report as well. In Asia region, we are number 5 after New Zealand, Japan, Australia, and Korea. Not too bad, our position. Yeah? Out of 108 countries, we are number 33. We are quite a high ranking in terms of in Asia, in Asia countries. Yeah. Next slide, please. If you compare back in before 2020, in 2019, we were ranked number 51. So we have improved. Right? Next. Yeah, or that on the Trilemma ranking. But this is, again, we also were ranked by World Bank in doing business ranking. So in terms of one of the criteria that World Bank annually assess, what they call getting electricity, we are ranked high number 4 after UAE, Korea, and Hong Kong. So there are various parameters that they use. So one of the parameters they use in terms of time, procedures, in terms of reliability of supply and transparency of tariff. Do we actually consumer being charged on the tariff? How transparent that particular country? In terms of reliability, in terms of interruption index, SID, and so on and so forth. So we are ranked number 4. Quite good, I would say. That of course we continually improving. We strive to go higher and higher. Maybe one day we rank number 1. Yeah. Next slide. So that rank is out of 190 economies, our countries in the world. So when we do this planning ahead, when we do the projection in terms of how we plan for developments of power plants, of course, the first input is the demand. We have to forecast the demand. And so if you look at this plot, the curve on your right side, we have different colors of curve. So if you look at the black, the solid black color, this is the actual, the historical, the actual maximum demand growth or value previously before 2020. If you look at this solid red curve, that's the demand without renewable energy, the total electricity demand at the grid level. And the blue dotted is the demand with renewable energy at the distribution level. So you can see that there are two wire, or there are two level of grid, either connected to transmission, the high voltage, in our case, 132 kV and above, and also at reticulation voltage or distribution voltage, 11 kV and 22 kV. So that differentiate between two curve. Yeah? So in total, actually, there are, you can see growth. The total growth, although not as big as before, but still growing. The demand of electricity is growing, 0.9% on 2021 to 2030, and 0.17% for 2031 to 2039. That's the maximum demand, or peak demand, still growing. The net electricity demand is projected to grow 0.6 the same period, 2021 to 2030, and 1.8 2021 to 2039. So net electricity demand will be used for the Peninsula Malaysia for our plan. So let me try to explain the difference between the net and the gross. So the blue dotted is the demand that we use in the plan that what we call that we finalize in the report. So the red solid curve is the total demand. Because why? Because when in centralized planning, you actually plan for the development of power plant at the grid level, at the 132 kV voltage, 275 kV voltage, even 500 kV voltage. So that you see the demand at those voltages. But this emerging technology, the solar rooftop and the emerging distributed energy resources at the reticulation level, that actually suppress that demand. Or in other words, that demand by customer at the very end of the supply chain being served by this distributed generation. So at the grid level, they don't see this. That's why the net that we use to plan for centralized generations asset or power plants. So that's the difference between the red solid curve and the blue dotted curve. Next slide, please. Yeah. In order to meet, this is the policy set by the government. We as Energy Commission, the policy being decided by the policymaker, which is the government, they have set a target. By 2025, we want to increase the renewable energy capacity from today, it's about 17% to 31% in 2025. Not too far from today, year 2021. So to meet 31% renewable energy capacity for Malaysia, and for Peninsula Malaysia, equivalent to 26%. So we need a new renewable energy capacity. So in total, we need 1,178 megawatt new renewable energy capacity by 2025. So you can see that we have we have the breakdown of this renewable energy capacity. How much is the solar capacity? How much is non-solar? So for solar energy, we plan to add about 1,100 megawatt, and the rest is for the non-solar. So in this particular plan, we have redeclared large hydro capacity as part of renewable energy resources. This is aligned with the international standard. And if you look at the what we call waterfall or the bar chart on your right, so the one the dotted rectangle, that the new capacity that we have to add in order for us to achieve target of 31% by 2025. So we are doing okay. We are doing good in terms of meeting the target renewable energy capacity by 2025. 20%. So we have several programs, which I will explain later on. But again, before I move into the next slide, just the last point on your left, a study to examine and identify the flexibility and threshold of renewable energy penetration in the system currently being conducted. I think I'm sure in your lecture, in your research, this topic is very important. We cannot ignore that, as we increase a share of renewable energy, especially a share of what we call VRE, variable renewable energy capacity in our capacity mix. We have, gas-based plant, we have coal-based plant, we also increasing renewable energy capacity. But in particular, in our country, in Malaysia, we have a lot of we're going to increase a lot of weather-dependent renewable energy capacity, which is solar. So as what we call it, this VRE increases. So we have to make sure the grid is ready, the network is ready to accept more and more variable renewable energy capacity into the system. That's why, in order to make sure we can maintain or we can keep the security or reliability of the supply, so we have to identify, all this enhancement or modernization of the grid. So we are conducting. We have still not finished this study. We're conducting the studies on the impact. So I will anticipate there will be a finding in the studies that we will adapt or adopt. We will implement, especially I'm sure you have heard about this dark curve in California and issue of variability of renewable energy, especially solar and wind, that we have to manage. We have to make sure will not have severe impact on the reliability of the network. So that's one note that I cannot skip, but have to mention this in this presentation. Next slide, please. Yeah. So beyond 2025, moving forward, so you may ask what will happen after 2025. We are moving. We are progressively move forward toward achieving, less CO2 emission. So as far as this 2020 plan, our development plan, we are moving toward 40% RT capacity by 2035. So we will project by 2035, the whole Malaysia will have a 40% capacity. For Peninsula, in particular, we have 31% renewable energy capacity. So we have more RE mix in the power or electricity mix, 2,404 megawatt by 2035. On top of, I mentioned just now, 1,100 megawatt by 2025. This is on top. Yeah? So again, we have to make sure the grid is ready with all this VRE into the system. And of course, I'm sure you all are aware of the possible solutions, especially battery storage and so on. So next slide, please. Yeah. So if I can break down, I mentioned just now the mix of capacity at the moment. We have certain percentage of gas, coal, and renewable energy. So moving forward, you can see the bar chart on green. We are increasing the renewable energy as we move forward. The first phase is 2025, and the next phase is 2039. So as the renewable energy mix increases, so we have to bring down what will reduce is a coal capacity mix in the system, as well as the gas also will take over. You know that coal emit double CO2 if you compare to gas with the same unit energy or kilowatt hour that each technology produce. So beyond 2030, there will be about 1,000 megawatt of new thermal and renewable energy capacity required. You can break it down into 1,000 renewable energy and thermal 9,000. So having a thermal generation capacity is crucial in maintaining generation reliability and adequacy in the system. Of course, when we do a planning, we have few criteria that we have to comply with. One is the HHI index, diversity index, concentration index that we have to comply. What else here? So yeah, this basically a trend or the plan that we have beyond 2025 up to 2039, the capacity mix projections. Next slide. Yeah. So what what will be the impacts on the reserve margin? You know that the reserve margin definition is anything, the capacity, anything beyond the maximum demand that we have, those are the capacity in excess of the maximum demand. Those are the reserve margin that we define as a reserve margin. So at the moment we have plenty of reserve margin. Of course, to reach the optimum level of reserve margin, we are targeting by 2030 to bring down the reserve margin to 26%. So it is also important that new capacity is added into the system through competitive bidding process to ensure optimum reserve margin. Yeah, that's how the policy is. I'm sure, especially in Malaysia, you're aware that early, I think this year, we awarded large-scale solar development project to the winners of our open tender competitive biddings. So that's always our policy, to conduct bidding or open tender process. And why we need reserve margin? Because despite the capacity in excess of maximum demand that we have, the plant can go wrong. Can be in force outage, can go wrong without plan. We have also to allow some plant to go on an outage on maintenance for their maintenance outage, maintenance schedule. So those are the reserve margin that allocated to all for those outage schedule there. Next slide, please. Yeah, in renewable energy capacity in Peninsular Malaysia is expected to increase to 30% by 2039. The share of renewable energy capacity is projected to increase. I think I already mentioned 17% today or this year to 31% by 2039. So you can see the different color. So the green color will increase, which is the renewable energy capacity will increase at the expense of the black or the gray, dark gray color at the bottom bar chart, which is coal capacity. And the gas will increase, the gas capacity will increase. That's how we can achieve reduction of CO2. I can show you later on in my presentation how we actually plan to achieve the COP21 pledges. So you can see the share as a share of renewable energy capacity increase. The coal mix will reduce, obviously, but the gas will increase slightly. So share of thermal capacity will reduce from 82% to 69% by 2059, with coal reducing from 37% to 22%. So we are less dependent on coal-fired power plant to serve the growing demands in future. Next. Yeah, of course, you cannot avoid, part one of the triangle is affordability. So we have to, calculate the system, the total system cost, the fuel cost, the power purchase agreement, the capacity payment that we have to pay. We are under a single buyer model, our industry, the electricity supply industry. So we have a long-term contract that are signed by off-taker and the IPPs and developer. So these are the costs we have to take into consideration. Of course, as the demand increases and generation have to meet those demand increases, we have to have more power plants. And of course, with more power plant come with fuel. For thermal power plant, we come with fuel. So we have to pay for that fuel. Of course, for the solar, we don't pay for the fuel, but we have to pay for the upfront capex. So these are the costs. So in tandem with the increasing demand, we are projecting an increase of it's about 52.53 billion by 2039. So these are the costs will be reflected in the end consumer tariff that all the consumer for electricity in Peninsular Malaysia have to pay. for this annual or for the total generation cost. Next slide, please. Yeah, I just want to comment on the average. We still have a percentage, a big percentage of gas power plant in the capacity, electricity capacity mix. If you look at the projection on the gas capacity mix, of course, from 2031, we see a decrease or plateauing, decrease. But as we decommission big coal plant in 2030, so that will be replaced largely by gas plant. So you can see the uptake increase of gas power plant starting in 2029. And then it will keep increasing until 2039. You can see that, as I mentioned, as we are being less dependent on coal, the gas power plant will take over. And of course, with renewable energy capacity increase, the share of RE will increase as well. Yeah? So that on the projection for the natural gas demand for this under this power development plan. Next target. Yeah, this is very important. What is the driver? What's our aim? One of the trilema to meet the target of 45% reduction of carbon intensity over GDP. So those are the plans that I mentioned: increasing renewable energy capacity, being less dependent on coal plant, and all the program that we have, large solar plant, and we have a net energy metering, feed-in tariff program, self-consumption program, and we have technology, not only solar, we have a biomass, biogas, hydro, mini hydro, medium-sized hydro, large hydro. So that enables us to meet. By 2030, we can, at least in the power sector, in the electricity sector, we will meet the 45% reduction by 2030 with from the base of 2005. So those are the numbers of CO2 emission that we plan to reduce over GDP, the carbon emission intensity. So these are the driver, the main driver, how we come up with this plan, with the program going forward, 2025 and 2039. Yeah. Next slide. Yeah, so in summary, we have to consider the trilemma, balancing the trilemma, security, affordability, as well as sustainability, environmental sustainability. We had this pandemic last year, and also continuing this year. We have some reductions in demand due to economic impact on economic activities. These are the challenges that we have to face. But again, we can see, we can forecast, the V-shaped economic recovery, and as well, we have to get ready for this demand uptake, swing, sharp swing back on the maximum demand or peak demand from the industry, commercial sector, consumers. So by 2030, about 6,000 megawatt new generation capacity is required to meet demand growth, and also replacing retiring plant. This power purchase agreement will retire, so we have to make sure you have enough capacity to meet all the growing demands. It's also important that this new capacity is added through, of course, open competitive bidding to achieve optimum cost and affordable tariff to the consumers. So the share of renewable energy will increase, obviously, from 17 to 31%, and the share of thermal capacity will reduce from 82 to 69%, and the CO2 carbon emission intensity target for Peninsular Malaysia from the power sector expected to meet a 45% reduction by 2030, and further reduce 65 by 2039. So we are, as I mentioned, this variable renewable energy (VRE) technology, we have to make sure the grid is ready to receive, to have higher penetration, and also higher renewable energy integration to the grid, and making sure the grid still secure, the grid is still reliable, with increasing share of renewable energy, especially the VRE into the grid system, so the grid remains stable. So we have to plan for any mitigation. I mentioned battery energy storage, which is one of these mitigation on variable renewable energy. And okay, there's the plan actually been reviewed annually. The committee will sit in October, and we will, progressively looking at the new technology, new solution, new challenges, be it economic, be it social, as well as the technology or the option, the environmental sustainability challenges. Those are the factors that we have to take into consideration while doing this planning ahead for us to meet the growing demand and the growing economic growth for our country, while maintaining the balance of this energy trilemma, as well as meeting the aspirations of the government policy. I think with that, I will conclude for my presentation. Next, I guess this is my last slide. Yeah, I will conclude. I will happy to open for any question. Maybe I pass back to the Madam MC. Thank you very much.
Thank you, Encik Abdul Razik, for the sharing of the plans for generation of power in Malaysia. We have some questions from the audience, so I'll start with the first question posed. Encik Razib, with reference to electricity affordability, when can we expect reduced electrical tariffs? I think this is a question in the minds of many of us, actually.
I think if you compare around ASEAN or Asian countries, we among the cheapest. The cheapest, I think, is Vietnam. I think the most expensive, if I'm not mistaken, is the Philippines. So at the current cost of production of electricity, of course, utility, service provider, utility, the major utilities, the tenaga, the TNB. So we believe that is very competitive. But of course, we're looking at a future saving and future technology and possible saving that we will pass to the consumers. But as far as this our structure at the moment, we have a unique. We have a tariff structure that balance between the high consumer of consuming large amount of energy. I think they have to pay a little bit more, and the lowest consumer consume the lowest energy. I think they enjoying the rate which is much less if you compare to the highest consumer. Yeah. So that one aspect of our tariff. Of course, there are two components of tariff. The fuel cost. We are buying, we are importing 100% coal from overseas. This is subjected to a market price of coal. For gas, we have indigenous gas from Petronas gas. We also we have started importing LNG from overseas. So so those are the elements. I think about almost 60% the cost of tariff from the fuel aspect. of generation aspect, and the rest 40% from the wire, the reticulation, the transmission, the grid cost. So from that, we derive the tariff. Yeah. So those costs. So that's why you can see that recently government announced imbalance cost pass-through. So we maintain the rebate of 2 cents for all users. So those are the saving. So every month we have to look all the actual costs of buying coal, buying gas, cost of generating the energy. Then we have to align, or we have to look at the base. What is our base assumption when we set the ICPT 6 months preceding that? So we will pass all this saving to the consumer. The 2 cents that we are, including me, that all the consumers are enjoying, the 2 cents, actually the rebate that we give to all consumers, because we managed to achieve the cost reduction, especially the fuel. The fuel is the major cost factor in the tariff, kilowatt-hour tariff that we are paying. All of us are paying. So of course, this system we call incentive-based regulated IBR regime, where we set upon utility, which is TMB, that they have the cost of their capex and opex, their certain return that we control, we regulate. And we, every 6 months, we look at the cost of fuel. Then we pass any saving to the consumers in terms of rebates, or vice versa, or surcharge if the cost increase the preceding 6 months. So this is a mechanism that we already started since 2014, IBR mechanism and ICPT mechanism. Yeah. Of course, we always encourage people to practice energy efficiency program. We also encourage people to purchase minimum energy performance standard, the star rating on all those domestic appliance equipment like fridges, aircons, rice cooker, washing machine, not washing machine, TV, your flat TV, your screen TV. So we encourage people to save LED lights, encourage people to save energy, as well as we have this rooftop net energy metering program for all consumers. We also encourage people to participate in their own solar generation on their rooftop. Yeah. So these are the options. Other than the tariff that we regulate, these are the options to the consumers to save and to self-generate their consumption or their demand on their rooftop. So those are the initiatives governments are doing. Of course, we have future initiatives that we'll announce from time to time. Next question, please.
Okay, we have another question. I think I may have to rephrase the question. Assalamualaikum Tuan, very good presentation. Just to feel, it's been removed. Okay, just to feel how our renewable energy share projection compares with our Asian neighbors. So I think he's asking how does our efforts compare to our neighboring countries, I guess.
Not from top of my head, but we have our own aim. As I mentioned, the COP21, and also government set a target policy. I can compare with Singapore. I think Singapore have limited renewable energy resources. They are heavily dependent on gas, fuel. They don't have a coal power plant. I'm not sure about Thailand. Thailand, they also aggressively pursuing. They also pursuing. We have under ASEAN target of, I can't remember from top of my head. ASEAN also have some target, so we also contributing to the ASEAN target in terms of renewable energy capacity as well as carbon emission. We also look at other countries like Vietnam also aggressively pursuing renewable energy, especially solar. I'm not sure about Philippines. They have geothermal. That's one of their advantages. Of course, they have wind as well, and Thailand they have a wind. We don't have a wind. We don't have enough wind resources in our country other than a small area in Kudat in Borneo. Of course, some other private entity exploring offshore wind farm in offshore peninsula coastal area, offshore peninsula, Malaysia. Whereas a country like Laos, they have rich water, dam, hydro resources. We have limited hydro resources in Peninsular Malaysia. Of course, we have still potential in Sarawak, hydro potential in Sarawak. Other country like Brunei, I think they are limited. Brunei limited to gas, but they also have limited demand. Other country, Thailand, Laos, Vietnam, Cambodia, as well. We are okay. We are part of ASEAN target. We also are contributing toward achieving ASEAN target as well. Okay.
I think we'll have one more.
Okay.
And I think we'll take this one related to your sharing of the energy trilemma, because that's quite interesting. So on the energy trilemma, energy transition and future of coal, does this plan consider the need for energy transition for future sustainability, and what are its challenges?
Yeah. That's why maybe I forgot to mention the word transition. We are transiting. We are transitioning toward sustainability or sustainable mix. You can see that the share of renewable energy actually increases significantly, and our dependency on coal actually reducing. Today, we have significant percentage of coal, but it will reduce, and coal plant will expire. We replace with gas plant and of course renewable energy that will contribute significantly to reduction of CO2 emission. Right? So the challenges is balancing the affordability, the cost. At the moment, of course, the cheapest I can share with you in terms of kilowatt hour, the cheapest still coal fired power plant, and then followed by the gas, and followed by renewable energy. You have to look at the total cost, because as I mentioned, as you increase a share of particular technology of renewable energy, which is VRE, variable RE, you have to spend more investment on strengthening the grid, because this weather dependent, RE resources, we have to make sure we have to spend some capex on strengthening. And we also moving to a decentralized system from a big power plant toward more distributed generation. So this poses a challenges, because as the classics of a power system is a one-way flow. You have from grid toward the end consumers, transmission, distribution to the end consumers. Now we have a biflow with distributed energy resources coming from at the end of the supply chain or the value chain. So we have to manage the two-flow system. And on top of that, with this variability of the resources, we have one challenge. We have existing challenges of variability of the demand. We cannot stop people of switching on and off their supply. That will impact the variability of the demand. But now we have additional challenge. The variability of the resources. We still have what we call dispatchable plant. We know how much coal we have at the coal yard, next to the coal power plant. We know how much gas we have in the pipeline. We can control the resource, the generation, or dispatchable. But when you add more and more weather-dependent renewable energy resources, these are the challenges. So we have to make sure, the trilima, the security is very important. We can afford, as as we are moving toward more electrification. We used to have only diesel train, and now we have electric train. Now we have a long distance electric train. Now we're going to have more EV car, less combustion cars, and so as the whole sector of economy moving toward more electrification, we have to meet all this demand, as well as the technology of energy generation toward low emission, low carbon generation. So these are the challenges. So that's why we have to crack our head. We have to strike a balance, a proper balance. We have to make sure the supply will not be interrupted. So can you imagine, without even 1 minute of, not telling about half an hour, but even 1 minute without electricity, that will have a huge implication toward the economic activities, the security of the countries, and so on. So we can afford. Maybe people take for granted. It's not as easy as flipping a switch. There's so many activities involved along the value chain. So I'm not saying that we are the only one can do this. Of course, we strive to make sure the energy is secured all the time, 100% all the time, 24, 7 days. We have to make sure the energy the cost that we can control the cost that the consumer will pay at the end of the day, and also meeting the low carbon emission target, meeting sustainable future for this sector. So these are the challenges. I don't say that there is no solution. There are solutions. There are associated costs with it, and we are moving the pace that we can afford. So and also we are meeting the target of COP21. That's very important. In the country perspective, Malaysia perspective, we are part of the country that already pledged to meet the COP21. We're moving toward that. We are planning toward that, as well as striking the right balance between those objectives of trilima, energy trilima. I hope I answered your question.
I think that was a very good explanation on the challenges in this trilemma. I think that's all that we have time for in terms of Q&A. Before we move on to the next plenary speaker, we would like to request that we take a group photo. I think the host will somehow bring everybody to the main stage for a group photo.
Tengok kamera later.
The second plenary speaker, Professor Ma'amar Batayab, are you there? Can you switch on your camera? Okay. So I think the host will bring all the presenters onto the main stage for a group photo. Unfortunately, the chair of the department, he's experiencing very bad weather at his home right now. So his internet has been cut off because of electricity is down. So power problem.
Are you sure? I mean, I have to make a call to the
Yeah, he
provider
told us
electricity.
that he kept it's because of the lightning. He told us. So
Okay.
yeah, that's normal.
We'll check on that.
Okay. All right. So I think the host will take the picture. So maybe I'll just count. 1, 2, smile. Okay, I think that's okay. Let me check.
Where he lives? He lives in Perak, somewhere in.
No, he's
Ipoh?
in Batu Gajah.
Okay. Right.
So that's a different district actually, even though it's quite near.
Okay.
Hold on. Let me check whether the photo has been taken. because I'm not getting any messages from the host. Ah, okay. Yep, we've captured the moment. So should be okay now. So thank you very much once again to Mr. Abdul Razib for the very informative presentation, as well for responding to the questions that have been posed by the audience members. So we will now move on to our second plenary talk. So before we move to the second talk, I would like to remind the audience again, because I know that some of you have just recently joined, that if you have any questions to be asked to our distinguished speakers, you can do so by using the live Q&A button located on the control panel at the bottom of your browser. Okay, so you will need to type up your questions, and we will look at the questions and select some to be forwarded to our plenary speaker. Okay, all right. So we will now move to our second plenary talk. But first, let me introduce him, the speaker. Professor Ma'amar Batayab received the BS, MS, and PhD degrees in electrical engineering from University of Southern California, Los Angeles in the US in 1976, 1978, and 1981 respectively. From 1981 to 1982, Professor Batayab worked as a research scientist at the Bel Air Research Center at Shell Oil Development Company in Houston, Texas. And his work was on the development of seismic signal processing deconvolution algorithms for gas and oil exploration. He then directed the Instrumentation and Control Lab of High Commission for Research in Algeria between the years 1982 and 1988. In 1988, he joined the Electrical Engineering Department at King Fahd University of Petroleum and Minerals, Dhahran, Saudi Arabia, and he has been professor at University of Sharjah, UAE, since August 2000. At the University of Sharjah, his portfolio includes being advisor to the Chancellor for Graduate Studies and Scientific Research, the Director of Research and Studies Center, and since September 2014, Professor Batayab is the Vice Chancellor for Research and Graduate Studies at the university. Apart from his academic roles, he has been consulting for the petrochemical industries and has been involved in various R&D funded projects in the areas of control and signal processing applications. We are therefore very honored to have him here virtually as our second plenary speaker. We now invite Professor Ma'amar Batayab to deliver his talk entitled Model-Free Robust Approach to Complex Systems, Active Disturbance Rejection Control.
Thank you very much for the introduction. Do you hear me?
Yes, we can hear you.
Excellent. Can I share my presentation?
You may.
Yes, please. Okay. All right. Can you see it, please, the first page?
It's not coming up yet.
Oh, maybe I didn't share. Let me share. Okay. Yes, let me share first. Here it is. Where is share screen? Yes. Okay. Share screen. Now share. Yes. Okay. No. What is it? Let me repeat. Share. Where is share screen? Okay. Stop sharing and let me share again. Share screen. What is the presentation? Share. I'm looking for the presentation. Where is it? Yeah. Okay. I want to share. It's showing me only entire screen. No. Okay. Share. So how do I share the thing? Can you see it or no?
Not yet, but if you look at there it is. It's coming up. I think maybe there's a bit of delay. Okay, we can see it fine now.
First page, right?
First page, yes, with
Excellent.
the title. Yep.
Excellent. Bismillah ar-Rahman ar-Rahim. Good morning, good afternoon, and good evening, everyone. I assume it's an international conference, and therefore it's people from all over the world. It is my pleasure to share with you some research I have done the last decade or so with an overview of what also other people did in a model-free, robust control approach to complex systems. And I will emphasize on one particular recent technique called active disturbance reduction control, for which I have some contribution with my research group. So I will, the outline of the talk is I will motivate first the problem we have of modeling and control, and then I will mention briefly the advanced control techniques that are available to solve partially some of these concerns and challenges. And then I will motivate why active disturbance reduction control is promising to solve many of these challenges. And then as I will be combining it with fractional modeling and control, I will briefly introduce this concept and then show a prototype of 2 or 3 new results we have in this area, and then motivate our audience by the various applications and promising research directions that are available to be taken in this area of adaptive or ADRC. And then I will, in a more general context, I will mention where is going advanced control for the next, let's say, 50 years. So I will start with a motivational note. As you know, nowadays, there is a high competition in producing, marketing, and selling products. And therefore, these companies or entities that are producing so many products, they need to be optimal in many, many aspects in order to compete. So they need an increased throughput to be able to have a good balance of budget. The quality of the product has to be very high. Then they have to be tight in using raw material and with efficient energy utilization, as well as taking into consideration the issues and problems we have in environment, pollution, and safety. Here are the challenges that motivated me a few decades ago to start working in this important area of what we call model-free control. Model-free control meaning you design a control system without knowing the details of the model, the dynamic model of the physical system. Because in some situation, it is very difficult to know the detailed model, as I'll give you two examples in a few minutes. But what prevents you from knowing exactly a model are many of these things I am listing, these challenges I am listing in this slide. Many physical systems, such as thermal systems, they have delays in the process. Communication network, you have delays in the message, in the data. And sometimes this delay is unknown or random or uncertain. So you don't know it, and hence you will not be able to model it. What complicates more, some physical systems on non-minimal phase, and this is a phenomena, meaning the system has zeros in the right half plane, and therefore it's difficult to control, much more difficult to control. And sometimes you don't know beforehand that your physical system is non-minimum phase. You have complexity in modeling for so many reasons. Take a chemical reactor, you mix up things, and what is the density of the new product? It's not, sometimes it's not evident. Suppose you have a spacecraft in space and you go out of the atmosphere. You may be in a situation where the gravity changes and many other things change, and therefore you don't have a well-known dynamic behavior of these spacecrafts, for example. You have uncertainties in the process dynamics. Very often you have uncertainties in process, in any electronic circuit, in a power system, in a communications. You have many uncertainties. Noises, the least you can have is you have the what we call thermal noise in electronics, that is random, that you cannot predict it. You have raw material quality fluctuations. You have many fluctuations in raw material that is the input to any control system. And therefore, you have a changing process and changing conditions of the process. And the controller needs to know these changes to be able to correct for the changes to meet its objectives. And this is not evident. You have disturbances, internal and external disturbances. You have unmeasured variables. There are variables you cannot measure in many situations. Either they don't have sensors, or the sensors are very expensive, or in a nuclear situation, you may not reach that place where you want to put your sensors. You have noises, as we said, electronic noise, mechanical noise, interference, etc. You have time varying parameters. We have many parameters that vary with time, and therefore the process and the model becomes much more complicated. You have nonlinearities in the process, and it's very much more difficult to control a nonlinear system and design controllers for it. You have constraint in a physical system. You cannot apply any input you want. You cannot reach any point of your system you want. So you have constraint. You have constraint in energy. You have constraint in voltage. You have constraint in position, in speed. You have constraint in many situations. And sometimes you have a multivariable plant or process, such as a petrochemical plant, a refinery, a distillation column, where you have many inputs and outputs, temperatures, pressures, humidities, positions, and interacting between each other, and every loop affects the next control loop, and therefore makes the problem difficult. And last but not least, you have multiple timescale systems where in the same physical system, let me give you an example, a fuel cell. In fuel cell, we have a thermal phenomena, a mechanical phenomena, an electrical phenomena, an electrochemical phenomena. So the time scales, the time constant, the dynamic behavior of fuel cell goes from 10 to the -6 of seconds to a thermal 40 minutes or hours. Therefore, you have to design a controller that can react as slow as 40 minutes to correct for dynamics, and as fast as milli or microsecond to compensate for an electrochemical behavior, dynamic behavior. So this is not trivial at all. Let me give you two examples. Of course, there are hundreds. Two examples why these problems I just mentioned, challenging problems of noise, uncertainty, interference, etc., are intrinsic within the problem, and therefore you have to find a control design that does not assume an exact knowledge of the dynamic behavior of your open loop system or plant, and therefore you have to design a robust controller without knowing the model, without having a physical or physico-chemical or mathematical representation of the differential equation, for example, governing that system. Here is typical. You have a plant, call it a refinery, call it a a transformer station connected to actuators and sensors, and it is controlled by many controllers, but the controllers are 1,000 kilometers away from the plant. This is happening today. It exists in many places. And therefore, you need to control a process somewhere, a plant, by a controller elsewhere through a communication channel, through internet, for example. You could imagine how many challenges you have. You have challenge of connectivity. You have challenge of limited capacity. You have challenge of all kinds of interferences from other networks or other signals or other systems. You may have congestion in your network. You have quantization. You have possibly a random delay or unknown or random delay of your data, and you may have a packet loss in your communication channel. So all of these are uncertain, unknown phenomena that you have to take into consideration, and therefore, in general, you don't have a dynamic behavior of these control systems for signals going to the actuators and coming from sensors going to the controllers to meet the objective of the plant. The second example is in renewable energies. Look, here is a typical power demand profile for energy, for power. But look, the solar irradiation that determines the behavior and the efficiency, the productivity of your plant, look, it's very different from this. It is random. It is unpredictable very often. You could have cloud and the situation is more difficult, etc. Same thing for wind. Look at the wind profile. The wind profile, sometimes it's not there at all. Sometimes it's very much available, and many times it's random. So how can you respond to a very well-known, scheduled in advance, forecasted well, scheduled in advance demand with these random available energies of temperature, wind speed, and solar irradiation? So you can see that there are many uncertain, unknown interferences, disturbances that you have, and therefore you will not be able to have a good dynamic model of your renewable energy resource or sources to develop the controller that meets its objectives. Of course, for all these problems I mentioned, the challenges over the last 40, 50 years, people developed many solutions, many algorithms, many techniques. So there are some multivariable control techniques, such as decoupling control, LQR, linear quadratic regulator, linear quadratic Gaussian LQG, H infinity, robust control, all kinds. Decentralized control, optimal control, adaptive control, model predictive control. Now it's implemented everywhere in the industry. Robust control, nonlinear control, fuzzy logic control, neural network, expert systems, genetic algorithm, hybrid, fractional, chaotic. All of these are important techniques developed. They work in some situations. For some of them, the model does not need to be completely norm. For others, you need to have reasonable bounds also about the model, etc. We don't have time to go through this, but we would like to introduce a new technique recently, last 20 years, basically 20, 30 years, which was developed, introduced by Professor Han, J. Han from China in the 90s. Well, he did it in Chinese in the 80s, but it was published in the 90s in English. And it's called ADRC, Adaptive Disturbance Reduction Control. And what he said is the following. He said, I don't have a model. I don't have a mathematical model for my plant for all the reasons I mentioned. In those situations, of course, if you have a model, you should use it, of course. But in situations where I don't have precise model, or I have model with very big uncertainties and unknown parameters, or a lot of randomness, then I need to do something. So he said, okay, what does a physical system has as uncertainty? It has internal uncertainties and external disturbance. The internal uncertainties can be parameter uncertainties or dynamic uncertainties, model uncertainty, and external disturbances that occur everywhere in the physical system. Some of them you can model, others you cannot. So partially for some of these types of disturbances, many techniques have been successful. Adaptive control is implemented in the industry for processes having unknown parameters, robust control with less degree for unknown dynamics, etc. However, you need a new control scheme to compensate for all these types of uncertainties, and that's what ADRC can do, and that's what Professor Han and his people after him, Gao and many others, proved, and nowadays it's being implemented in so many industries, many applications, and many industries adopted it as a solution to modern plants. So basically, Professor Han said, all right, I have a total uncertainty, which is all the uncertainties, internal parameter, plant uncertainty, external uncertainties, and I want to control the system with these uncertainties, which may be all kind, linear, nonlinear, time varying, or in time invariant, parameters, or all kind of uncertainties you could imagine. So here is the problem. You have a process. The process may have some internal uncertainties, external uncertainties, and of course, all the disturbances. So he said he's going to do two operations. What are these two operations? Using input and output data, input sensor, output sensor. So using input and output data, he developed an estimator called ESO, Extended State Observer. And with this estimator, he will estimate the disturbances. All these disturbances, he will estimate them from just input-output data of the process. And then once he estimates the disturbance, of course, he can correct for it. He can correct for it through a controller to meet the objective so that the output tracks the reference and meet closed loop performance, as well as reject all those disturbances. Very innovative idea developed in the 80s, 90s that is now gaining ground daily. So here it is, basically, the idea is to obtain a proper estimation, ESO, Extended State Observer, and I'll show you in the next slide why it's called this way. So, and I'll show you why it's second order system, external disturbance. You estimate the disturbance, and then you develop a control input so that you compensate with this inner loop. With this inner loop, you compensate for the disturbance. What you get here is already compensated for the disturbance. And then once you compensate for the disturbance, you have another loop, outer loop, so that you stabilize the overall system and you let your output track, for example, the reference signal. So meet your objectives. So here is how it works. Now, the basic idea is, he says, Professor Han said, I don't have a physical model. By looking at this equation, you think he assumed a model. No, not much, very little. Let me tell you. First of all, this y double dot could be y dot, y double dot, y triple dot, fourth order derivatives, nth order derivative. But he noted that most physical systems work well if you assume second order derivative, and ADRC work well. But if it's third order derivative, all you have to do is you add a state variable. So this theory, I'll show you the last slide, is valid for nth order derivative. So if your system is dominated by second order, you put second derivative here. If it's dominated by third, you put third order. If you don't know, it's okay. Put it second order, and those other derivatives are here. They are with the disturbance, everything else. 10th order derivative is here, and if you are careful in the design, it works well. If it doesn't work, you may go to third order, fourth order, and it will work often. So plus a linear combination of the input, BU. This B, you have to have an estimate. The only challenge we have today, two challenges we have today in ADRC controller design, is to start with a good estimate of B and have an idea of what we call here the relative degree of the plant, the relative degree of the system, 2, 3, 4. Is it 1, 2, 3, or 4? Once you know it's 2, you put y double dot here and have a reasonable estimate of B, and you will get good results. There is no systematic method today of choosing B. Many PhD theses was developed on this, but there are some preliminary results that tells you if you take B large enough, B is just an input gain. If you take B large enough, in general, it will work, but at the expense of large input excitation. So you start decreasing and till you get a reasonable one, but still people are attempting to get ways to systematically estimate the right B, the right input gain for your plant. But you can see this, there is no model here. It is a model, but you are not assuming anything. Everything unknown is here. This F is the total disturbance. It has the internal disturbance. It has the unknown dynamics, the nonlinearity, the high frequencies, the dynamics, the ARMA model, the disturbance, the internal, everything is in this F. W is just the internal disturbance. F is all types of uncertainties you have in the model. So you need to estimate F. Once you estimate F, you correct for it and you develop a control to meet your objective. So how do you estimate F? Here it is. This is the main contribution of Han. How there? He said, okay, let me define the output of this open loop system to be state variable x1. Therefore, its derivative is x2. And hence I have x1 dot equal x2. And from here, x2 dot is y double dot, x2 dot is y double dot. It's f plus bu. So now I have second order state equation. Now, here is the trick. This is the innovation. The big innovation that made ADRC is this. He defines a state variable as the total disturbance. Everything you don't like, everything you want to eliminate, everything you don't know, everything that is uncertain, define it as state variable and then estimate it later. Define x3 as state variable f, which is the total disturbance. And then introduce it here. Since you define state, you need to add a third state. The third state, its derivative, h is the derivative of f. It turns out that h, we don't need it even later. So now you have a third order linear system. Look at this. This is third order linear system. You develop for it a third order linear observer. It's just Luenberger observer, for example, any observer. So this is a simple Luenberger observer of this open loop dynamics. So you develop Luenberger observer like this. So S is the gain of the observer. S is the gain of the observer. What is it? S is S1 S2, S3, because this is third order. So you need to develop or to design the three gains of the observer, S1, S2, S3. And of course, there are many ways to do it, and you have to find a compromise between the speed of response of your observer and the noise sensitivity. You don't want your observer to be too fast, because then it will be sensitive to noise, and you don't want it to be too slow, then the state will not, the estimate will not converge to the state rapidly. So people, Gao and others, developed ways to place the closed loop poles of the observer at some observer bandwidth, we call observer bandwidth, that is reasonable enough, not too high to avoid noise sensitivity, not too low to have enough conversion speed of the estimate of the state to the true state F. And it turns out to be a very simple design with one parameter. Look at this, tuning with one parameter. You tune your observer with one parameter, omega 0, called the observer bandwidth. So wrapping up the whole thing is, here it is. You use the input online, you are doing this real time online. Your physical system is running. You, through sensor, you got output data. Through sensor, you got input data. Using input and output data and the ISO model we just saw, third order model we just saw, third order model we just saw before. Where is it? Yes. Yeah, third order model ISO with third order observer. You get the estimate. X3 hat is the estimate of F hat. Observe the disturbances. All total disturbances are here. Once you observe them, you can compensate for them with this inner loop. With this inner loop, which is this, U equal 1 over B hat minus X3 hat plus U0. This is it. This is the inner loop. This is exactly this. Then you replace this U, you are applying to your physical system here, and magically, if X hat 3 converge to F and U0 and B B hat is a good estimate of B, magically everything will cancel. By putting this U here, everything will cancel here, and what do we get? Y double dot equal U0. Look at this. Y double dot equal, you compensated, Y double dot equal U0. All of this becomes Y double dot equal U0. Where is the unknown F? Nothing. Y double dot equal U0, it's a double integrator. There is no dynamics. There is no uncertainty. All you end up with by doing this estimation, then compensation, you end up with a new dynamics that independent of parameters. Y double dot equal U0, double integrator. All of this is double integrator. So for this double integrator, you use, for example, a PD. This is a PD, proportional derivative controller. Why derivative? Because x2 is x1 dot. So this is a PD. This is double integrator. With the PD, you stabilize the double integrator, and it's easy for it because double integrator, the parameters, F is gone. F is gone. Look at this. Double dot equal U0. There is no parameter uncertainty anymore. You, through this inner loop, you eliminated it. This is after, of course, as I said, assuming your estimate converge to F and your estimate of B is the right B. Once you do that, then all of this becomes a double integrator that has no parameters, and trivially with a PD, you stabilize the whole system and you let y track the reference with all the performance you want on overshoot and settling time and rise time, etc., as we'll see later. So therefore, if you have a good estimate of f through the SO, extended state observer, and if you have a good initial estimate of the system gain, then you have developed a robust ADRC, controller. Why? Why robust? Because of this. Look at this. You are controlling a double integrator. There is no parameter uncertainty. There is no disturbances. They are gone. All right. So, oops, what happened? It doesn't go anymore. Okay. Oops, I cannot go anymore. Ooh. All right. Ah, yeah. All right. So here it is. So this is recapitulating. So as I told you before, this is valid for nth order. This could be nth derivative. And once you correct, this is what you get. Once you correct for that U0, this is what you get. You get an nth integrator. Okay? And then all you need to do is, here it is, with the extended state, you are going, this is how you reject, as we said. And then here is, so this one is the assumption you have on your original system. This is just this equation. You estimate the state and reject, compensate for the thing. All of this inner loop becomes what? Nth integrator. Nth integrator. So now it's easy to control this. There is no parameters to eliminate. You just have to stabilize this with a PD. All right. Now, this was about ADRC. Now, what I did in my work is, and my group, is many results were existing in ADRC the last several years. So we wanted to do something new. So we developed what we call fractional ADRC. So let me go quickly. What is fractional operator? It's the generalization of first derivative, second derivative, third derivative, first integral, second integral. So instead of saying alpha equal 1, first derivative, no, I say alpha equal 1/2, half derivative. Alpha equals square root of 2, square root of 2 derivative. Alpha even can be a complex number. They call it fractional derivative. So there are 3 types of fractional derivatives. But as long as you are consistent, you can use any one of them. What does it mean? I have to go fast because I'm running out of time. What does it mean to have fractional system or fractional dynamics? In time domain, you are going from the normal exponential behavior of differential equations, the eigenfunctions, to hyperbolic behavior. It's much more general. And in frequency domain, you are going from that minus 20 dB per decade slope of a pole or plus 20 dB of a zero to a fraction of that. So you can have 10 dB, 5 dB, etc. And in terms of memory, you are going from short memory. Differential equations have so short memory. For example, a second order RLC circuit will have a memory of 2 units. But fractional systems have long memory. Of course, you could, differential equations are similar. Instead of having integer derivatives, you have fractional derivative. Alpha and beta can be any real or complex numbers. But what's important now, if you have a plant and if you have a fractional integral and fractional derivative, you see, if mu equal 1, this is first derivative. If lambda equal 1, this is first integral, and this will be a PID controller. But now it's a PI lambda d mu controller. So if you design also lambda and mu, then now you have 5 degrees of freedom. 1, Kp, Ki, Kd, that's 3, lambda, mu, 5 degrees of freedom. And instead of choosing a P, this one, PD, this one, pi this point. Pi this point, you can choose with mu and lambda anywhere here between 0 and 2, and you have infinitely many designs of the famous pi lambda d mu, and therefore you will have 5 degrees of freedom. Therefore, you can meet 5 performance objectives, and you will do much better than the classical, what we call integer PID. And I'm going to close with giving few examples of things I did with my group. With fractional order, we improved the linear ADRC, and we proved it by simulation and by experimentation. And the way we did it is by imposing the closed loop transfer function to have the Bode characteristic, Bode open loop characteristic, which is well known, so that it will have some robustness performance, and that robustness performance that says that the overshoot will be constant regardless of parameter variations. See, this is a property of the closed loop Bode transfer function. You change the parameters of the open loop system and the overshoot is kept constant. It's called the iso damping property. It keeps flat phase margin and constant overshoot regardless of gain parameter variations. So here is the trick we do. If you had an nth order system with ADRC, we add and subtract, because we want to develop fractional controller with 5 degrees of freedom. So we want to create a fractional state space. This is not fractional, this is integer. So we add and subtract a fractional. Lambda is fractional. So then we put these two in the other side, and they become part of the disturbance. Look at this. I have a new disturbance. Before I had F1. Now it's a new F, which is the original F1 plus all of this I added. Now, but what do I end up with? Look at this. This is a fractional state space. This is fractional dynamic equation because lambda is fractional. So then I can develop fractional estimator, fractional ISO, and fractional estimate, and then do the same trick of compensating for the disturbance and apply a simple proportional or state feedback controller, so that Y will track R, and I stabilize the system, I meet a certain overshoot, etc., etc. And magically, we applied it by simulation and experimentation to an inverted pendulum, and it gave excellent results. So we developed the fractional extended state observer. We developed the estimate of the state that will be fed in the state feedback, and we were able to get excellent performance. I'll just show you one performance where we compared the linear ADRC with the fractional ADRC. What is dotted is fractional ADRC for 3, 1, 2, 3, dotted 3 kp. The desired kp is this one, 50% increase in kp and 50% decrease in kp, meaning gain variation. And look, when you have variation in kp, the ADRC integer is not robust for the original one. What is it? Desired is the blue. Here is the true overshoot. But the minute you have perturbance or parameter variation, look, the overshoot you want. So this is not robust. But look, when we developed 1, 2, and 3, the hard lines are the fractional. Look at this, same overshoot. Same overshoot for the red, the blue, and red, blue, and black. Same overshoot, iso damping property via fractional. Another example, I'll have to go fast because I think my time is almost over. So this is another, all of them are 2021. So this is, we introduce with active digital message action a sliding mode. This way, here it is. In the observer, we introduced with the Luamberger observer, step-by-step sliding mode observer, and also sliding mode controller instead of the PD, and it gave excellent results. I will skip the results, but it gave excellent results, much improved results. And our last example is we applied the same ADRC with some modification to have some innovation on a robot, flexible link manipulator, and we got also some very good results. Look at this. We are tracking perfectly the step response. Perfectly, we are, this is experimental, tracking trajectory of the rigid band. We are perfectly tracking the system, the robot arm. All right, let me finalize next 2 or 3 slides. So this is to tell you that ADRC have been applied to so many applications, an infinite number of applications, and there is still, for those of you who I convinced today, you can really enter any area and can make contributions, and I will be very happy to help you start if needed. Also, many new directions of in ADRC. The stability, general stability problem for nonlinear system is still open. There are some partial results. ADRC tuning for nonlinear systems is a challenge. Selection of this N, the relative degree 2, 3, 4 is open. Tuning for B is still open. There are some preliminary results. ADRC for systems, of course, if you have some partial information, you should use it. How do you incorporate it in ADRC? ADRC, you need to develop controller that is fault tolerant. You need to generalize to switching hybrid systems that at the same time work continuous and discrete, such as system connecting to internet and others. 2 degrees of freedom ADRC, fractional ADRC, ADRC for network control systems, generalization to infinite dimensional system, partial differential equations, discrete time generalizations, and many more applications. All of these are possible applications where there is room for discovery. Of course, there are many other directions of control in the future. We are talking about integration of control, computing, communication, and networks, fault-tolerant and reliable systems. We need to design high-level control for decision-making, wireless sensors, network control systems, Internet of Things control, cloud control system, dependable control system, digital twin control system, and all the above. All of these are the control systems of the next 50 years or so. I thank you very much for your attention. I'll be happy to answer any question you have. Thank you.
Thank you, Professor Bataib, for that very interesting talk. And I think this can be seen by the number of questions that we are receiving from the audience. I suppose because your topic relates a lot to what many of our students are doing, because they come from different areas, and what you have presented seems applicable to all kinds of areas. Yeah. So I think I'll start off for the question, because this seems a bit like a mini reunion between you and one of our lecturers. So I'll start off with Dr. Syed Saad.
I am an old man, so I have many ex-students.
But he remembers you very, very well. So he says, thank you, Dr. Bataib, for the presentation. It reminds me of your DSP class at KFUPM, still as animated as 20 years ago. In the presence of system uncertainties and concept drift, maybe due to aging of the equipment, will ADRC be performing equally well?
Yes, because as I said, ADRC controller is acting real-time online. So it's using input-output measurements from the OPLU plant. Therefore, if there is any drift or aging of the equipment, it will, and hence it will be fed to the ESO. The effect of any aging through the sensors will be fed to the extended state observer, and therefore will be estimated online at every sampling interval. At every sampling interval, we are updating the disturbance estimation, and therefore we are also updating the compensation controller that does the job. Yes, it's at sampling interval we are doing the update of the data. Yes.
Okay, so let's move on to some of the other questions. I think they are from our students as well as staff. I'll start off with this. I'll continue with this. Hi, Prof. External disturbances or unmodeled dynamics are nowadays observed and estimated using disturbance observers or extended state estimators or ADRC. How is it better if we just consider the input-output relationship of the system or the transfer function as compared to state space model or the mathematical model with ADRC?
Yes. Yeah, that's a good question. Of course, if you have a dynamic model, if you have a transfer function of your linear system or the nonlinear dynamic equation of your physical system, of course, you probably should use another method. You can use any other nonlinear technique that develop controllers, such as nonlinear predictive control. Nonlinear predictive control is very powerful if you have state space equations or transfer function for linear or Volterra kernels for nonlinear. Of course, if you have a model, you should use available techniques, very powerful. I will tell you, linear and nonlinear predictive control is used everywhere now. But what I am saying is there are situations, many applications, where there are strong uncertainties in your model, and therefore those model-based techniques, such as linear predictive control, will not be able to develop the controller, because you need to make many assumptions on the open loop model that may give you the wrong controller because you have the wrong model. There is something called maximum entropy. Maximum entropy information tells you use as much information of your plant as you can, but don't engage on something uncertain. You see, let me explain. If you have a model and you don't inform your controller about an existing dynamics of the open loop, your controller will not be able to reply for it. But if you tell your controller, here is the open loop transfer function, correct for it, the inverse transfer function will correct for it very easily. It's mathematical equation. You can control for it. But at the same time, if there are uncertainties in that open loop transfer function or open loop state space, don't engage on something wrong, because if you engage on the wrong model, your controller will develop a controller design for the wrong model, not for your physical system, and hence it will do the wrong control. So this is maximum entropy. You have to find a compromise. If you have a certainty, you are sure about your model, definitely use it. Linear predictive control and nonlinear predictive control will do better than ADRC. ADRC is made for situations where you have uncertainty in the plant, randomness, unknown things, unpredictable things, that things you cannot model and that you can feed the controller with. Yes.
Okay, maybe we can fit one or two more. Let's see. Okay, another one. Thank you for the interesting talk, Prof. I have one question. If the same ADRC technique is implemented for any unmanned autonomous vehicle, how about the convergence rate? I mean to say, if it helps in tracking the desired performance faster as compared to current state-of-the-art approaches?
Yes, in fact, I have a PhD student who just started a few months ago on this. He's developing ADRC for UAVs so and drones. yes, from our simulation and testing on robots and preliminary testing on drones, yes, the ADRC algorithm is not complicated, especially the linear one. Linear IDRC is very simple. It's an equivalent to Luenberger observer and that simple controller, a PD controller. So it's not high computations. Therefore, in one sampling interval, you can do anything you want, and ADRC will work. Yes, we are within limits with no problem at all. Yes.
We have 5 more minutes. I think we can squeeze in one more question. We have so many. Because I find those related to your topic ADRC. Okay, I think we have one more. Hello, Prof. Great presentation. As the PIDs with ADRC scheme introduced 2 more degrees of freedoms, giving a total of 5 degrees of freedoms, it seems to me that the system now becomes more complex with additional parameters to be tuned. Is this correct?
Well, yes, it is correct. If you don't need to meet more than 3 objectives, don't use it. But I'm talking about a situation where, yes, sometimes we do want, especially with 2 degrees of freedom, sometimes we do want to stabilize the system. That's 1 degree of freedom. We want to control the overshoot, another degree of freedom. We want to control the rise time, another degree of freedom. We want to reject disturbance, another degree of freedom. We want to track a special reference step or sinusoidal input, that another degree of freedom. So you want to optimize. I want an optimal solution of my controller and many other things. I want to meet some constraint. I want to meet some surface, whatever. So yes, if you only need to meet 3 objectives, yes, the PID or the linear predictive controller will do the job. But we are saying you may have situations where your system is very complicated and you need to meet many objectives. Having 5 degrees of freedom is better than having 3 degrees of freedom to stabilize your system, track reference, and control overshoot, etc., etc. Yes. So it depends on the application.
So I think the thing that we can take away from this is it all depends on what your application is. Yes. and you need to look at the trade-offs and what are your requirements before you select a particular technique to implement. Okay, I think that's it. So thank you very much, Professor Batai, for the very interesting talk.
It was really my pleasure. Yeah.
Yes. With that, we have come to the end of our plenary session. So on behalf of the ICIAS 2020 Organizing Committee, I would like to thank our honorable speakers, Mr. Abdul Razib Dawood and Professor Ma'amar Batai, for taking time off their busy schedule to share their wisdom and knowledge to our participants. I would also like to thank Associate Professor Dr. Muhammad Naufal for his welcoming remarks. Unfortunately, he could not join us due to some technical problems with his internet connection, as well as a big thank you to those personnel who have worked tirelessly behind the scenes in order to ensure the smooth running of this session in particular and this conference in general. Thank you also to the attentive and cooperative audience. We have enjoyed receiving questions from you and getting them answered by our plenary speakers. And we hope that you will enjoy and benefit from the rest of the conference, of the virtual conference. So with that, I bid you Assalamualaikum and good night.
Thank you. Alaikum assalam. Thank you.